So an extension of those Pauline's rules for ionic ceramics, we can come up with a schematic for how anions and cations are put together in structures that's very helpful for looking at a vast majority of the structures. So we're going to look at that now. And so to look at that, we're going to start by examining close packed structures. So if you remember from 201, where we talked about structures in general, you will remember that FCC, face center cubic, and HCP, hexagonal close packed, are both close packed structures, and the only difference being the stacking of those close packed planes. So in FCC, it was the 111 that stacked in different ways. And then for HCP, it's the basal plane, which is the 0001 plane that's stacked in different ways, but those are both the close packed planes. So let's take a look at how those differences come about. So A is the sequence for a basic close packed plane, and if we then take another close packed plane and shift it, so in this case we're shifting it such that the one of the atoms is above one of these empty sites, these interstitials, right? So we shift it to that. So we call that B because it's shifted. And then if we shift it again and it goes back to the original configuration where the atom is right above the position below, that is what we see in HCP. So you see the hexagonal structure. So that's what we see there. And we're just cutting off some of these atoms just so you can see the stacking of it. And so that's how the basal planes in HCP are stacked. So A, B, A, B, A, B. That's how it continues. For FCC, if we take the same basic configuration on the bottom, and then we shift to B, so that's the same one as the B over here, but instead, if we now shift again to where instead of going back to the original position, it's still shifted over one of these empty sites to a third location called C. So this is what we see with the 111 planes in FCC. So we have an ABC stacking sequence of those close packed planes. And the reason I mention this is because our ionic structures are going to start with those arrangements, and then we're going to look at the interstitial sites, the tetrahedral and octahedral sites, within the vacancies of either FCC or HCP structures. So the for FCC up here at the top, we can see the location of the tetrahedral sites here in the 1/4, 1/4, 1/4 location, and then octahedral in the 1/2, 1/2, 1/2 type location. So coordination 4, coordination 6. So same thing with the hexagonal. Here you can see that it's not you can't see the hexagonal shape because we're representing it by a smaller unit cell, but you can still see where the tetrahedral locations are coordinated by 4 and where the octahedral locations are coordinated by 6. All right, so let's see how that schematic works. And so this is what we think of. We think of these ionic ceramics as having an anion an anion packing of one of the close packed structures, so either FCC or HCP. And then we take the cations of that ceramic and fill it into some combination of the interstitial sites, so tetrahedral or octahedral. So if we look at the cubic, which is FCC, so these ions are the anions in the close pack arrangement, and then we fill either the tetrahedral, which is shown by this 4-pronged thing, or the octahedral, which is filled by the 6-pronged thing. Some combination of those are have cations in them. And so this schematic of how we fill cations and anions gives us a huge number of the various structures. So if we take one of the the close packed structures with anions and then fill in some combination of the cations, it gives us a vast majority of the structures that you are familiar with. And so this is a table from your book. I had to cut off some of it, but it's table 3.3. And these are all of those structures. So you can see that the second column here is called anion packing. So you can see cubic close packed, which is another word for FCC. You can see distorted cubic close packed, so basically the same thing. Cubic, and then you can see hexagonal, right? So all of those are either based on cubic or hexagonal close packing. Then the coordination numbers are given along with the stoichiometry, right? So we talked about the Pauline's rules and how you get those anion and cation or metal, non-metal coordination numbers. So 6, 6, 3, so forth. And then the stoichiometry. So do we have a 1-to-1? Do we have a 1-to-2? Do we have a 2-to-1? So all of the different stoichiometries are shown in this column. And then this next one says sites occupied by the cation. So this is where the cations go in that close packed arrangement. And so in the first example, they all of the octahedral sites are filled with the cation. And then half octahedral are filled, half tetrahedral, and so forth, right? So you have some combination of those filled. And so this gives you a vast majority of these various structures: rock salt, rutile, zinc blende, antifluorite, wurtzite, nickel arsenide. All of these can be described in this manner. And so in the next sections, we will work through some of these binary compounds so that you can see all these different factors and see how this fits all together.